Okay, welcome back. What we're going to do right now is continue on with our chapter 27 lecture on magnetism. And what we talked about just before the end of the last lecture was this idea of forces acting on moving charges. So in other words, when you have some kind of point charge, let's say a proton or an electron, moving in a magnetic field, it experiences a force. And related to that, I want to review something called circular motion, which if you took Physics 44 or some equivalent, you learned about this all the way back then, which may have been over a year ago, so it's good to review. So circular motion. When we have an object that's moving in a circular path at a constant speed, we know something about the way it accelerates. It has an acceleration, and the acceleration vector points inwards towards the center of the circle. And what we call this is centripetal acceleration. So centripetal is just a fancy way of saying center seeking. So the A vector always points inwards towards the center. And on top of that, we know something about the magnitude. It's given by v squared divided by r. So that's centripetal acceleration. That's always going to be present for any sort of object moving in a circular path. Okay, well, if we think about that in the context of Newton's second law, okay, where the net force acting on an object is equal to its mass times its acceleration, we have to realize that m is nothing more than a scalar, just some positive number. So when you take a vector like A and you multiply it by a positive scalar, all that happens is you get a vector out which is in the same direction as the first vector. So in other words, F, the net force, and A, the acceleration, are going to be pointing in the same direction no matter what. That's always going to be true. So in this case, if you have an object moving in a circle, not only is the acceleration pointing in, but so is the net force. So sometimes we call this centripetal force because it's pointing inwards, it's seeking the center, it's the same kind of terminology. Okay, so a number of things to look at here then. We have A, shown in blue, pointing in towards the center of the circle. We have the net force, shown in black, pointing in towards the center of the circle. And then we have V, which represents the velocity of the object, shown in red, which is pointing tangent to the circle. So notice that the force and the velocity are at right angles. Okay, so when we actually apply Newton's second law to the radial direction, or what we call the r direction, we have to actually think about the sign convention. Okay, so the sign convention is this. We're going to consider any force positive if it points inwards, and any force negative if it points outwards, away from the center of the circle. So this is useful because when we add up all the different forces in the radial direction, some may be positive, others may be negative, depending on whether they're going inwards or outwards. But when we add them all together, when we take the sum of all the forces in the radial direction, we get the mass times the acceleration in the radial direction. And given what we know about centripetal acceleration, this is just nothing more than saying the net force in the radial direction is m times v squared divided by r, because that's our acceleration, v squared divided by r. Okay, so that's a review of circular motion for you. And why does this have anything to do with charges moving in magnetic fields? Well, I'm about to show you. So let's think about a point charge, just call that point charge Q, that's moving in a uniform magnetic field, so that's B, and it's going to have a velocity which is perpendicular to the B field. So we can set this up in a lot of different ways on our diagram, but how about we just say that the B field is pointing into the page, and the velocity vector, at least for the time being, is going to be pointing up. Okay, so B field into the page, velocity of the charge is going up for the time being. And so, if I want to know what the force acting on this charge is, well, it's given by QV cross B, as we saw in the last lecture. And there are two things to think about when it comes to QV cross B. One is the magnitude, and the other is the direction. Let's think about the direction first. Okay, the force, the direction of this force, since it's given by a cross product of two vectors, it's going to be perpendicular to both of those two vectors. So it's going to be perpendicular to V and B, which means we can figure it out using the right hand rule. Let's take our right hand, point in the direction of V, curl our fingers in the direction of B, which is into the page, and now your thumb is pointing to the left. So that's what we expect the direction of this force to be, just going straight to the left. So we've added a third vector to the picture, which is the force that's acting on the charge, and that's shown in blue. And that's going to the left, as we said. Okay, well, if you think about it, what we expect to happen in this situation is for the charge itself to move in a circle, because whenever we have a net force going one way and a velocity going perpendicular to that, we have circular motion. And that's exactly what happens. So the charge moves in a circle. Okay, in this case it's going counterclockwise. And notice that, again, the net force always points inwards. The velocity always points tangent to that path. Okay? So what we have is the charge moving in a circular path at a constant speed. Okay, this is really important. So to reiterate, whenever you have a charge that's moving, okay, perpendicular to a B field, its motion is going to be circular. It's going to move in a circle at a constant speed. Okay, so that's what we've gathered so far. If a charge's velocity is perpendicular to some kind of uniform magnetic field, it's going to move in a circular path at a constant speed. And now, let's try to say something a little bit more quantitative about this, and we'll start with Newton's second law. The net force acting on this charge is equal to its mass times its acceleration. So for the force, we're going to assume that the only force that's present is the magnetic force, QV cross B. So we're going to ignore gravity or anything else that may be happening. Let's just say the only thing happening is there is a magnetic force, QV cross B. That equals MA. Okay, well, when we have a cross product, again, we can think about the magnitude of that cross product as being, you've got the constant Q out front, you've got the magnitude of V, which would be the speed of your charge, times the magnitude of B, which is the strength of the magnetic field, and then sine of 90 degrees, because again, they're at a right angle. The velocity and the magnetic field are at a right angle. On the other side, we have m times a, but as we said before, we can plug in for the acceleration v squared divided by r for something moving in a circular path at a constant speed. And sine of 90, that goes to 1. If we solve for the radius, okay, so let's multiply on both sides by r, and then let's divide on both sides by qvb. That's going to give me mv divided by qb. So that's an expression for the radius of a path of a charge moving in this circular path in a magnetic field. That's the radius of that circle. Okay, we can take this a step further, because if we think about v in this equation, which represents the speed of our charge, it's the distance it travels per unit time, distance over time. And let's think of that in the following way. If I know what's moving in a circle, the distance it travels as it completes one full circle is the circumference. Okay, it goes around one circumference. So 2 pi r, let's put that in for the distance. For the time, I'm going to put capital T, which represents the period. That means how long does it take to go in a circle one time. That's the period given by capital T. And so if we solve for capital T, which is again the period of the motion, what we have is 2 pi r divided by v. Just cross multiplied by t, divide by v. To get the period is 2 pi r divided by v. And then what we'll do is we'll just plug in for the radius what we found just a second ago. And that gives us, so I have 2 pi over v from before. For the radius in these parentheses, I'm substituting m times v divided by q times b. To simplify, notice how the speed can be canceled out, and the period apparently doesn't depend on the speed. The period only depends on, well, the mass of the particle, the charge of the particle, and the strength of the B field. So we have 2 pi m divided by qb. That's the period of the motion. Again, that's how long it takes to complete one circle. And closely related to this idea of period is something called frequency. Now, if we think of period as how much time it takes to complete one full circle, think of frequency as the inverse of that. Okay, so in other words, think of frequency f as being 1 divided by t. And what does that actually mean? Well, if a period is the amount of time to complete a circle, then the inverse of that would be how many full circles do you complete per unit time. So for instance, a frequency could be like 45 revolutions per minute, RPM, or 78 revolutions per second. That's what we're talking about when it comes to frequency. That's the inverse of the period. Okay, so just flip that fraction and we get qb over 2 pi m. That's what we have for the frequency of the motion. Okay, so these are all very useful expressions that we're going to use in some calculations. And oh yeah, by the way, this particular frequency, okay, so the number of cycles, full cycles, a charge in a magnetic field makes per unit time, that frequency is called the cyclotron frequency. That's the name of it. Okay, now for a question for the class. So just to reiterate, what I want you to do here is try to work this out. You're going to use those equations that we just derived. And when you think you have an answer, come back to the video. So pause the video, work on this, then come back to it, and then we'll talk it over. Here's the question now. An electron whose charge is equal to negative 1.6 times 10 to the minus 19 coulombs and mass is 9.11, 10 to the minus 31 kilograms, is injected into this uniform magnetic field with a speed of 2 times 10 to the 7 meters per second, and let's say it's starting off moving to the right. The magnetic field points into the page, and it has a magnitude of 0.01 Tesla. A number of questions. What is the radius in centimeters of the path that the electron moves in? What is the frequency of the electron's motion? We'll give that in hertz. And does the electron move clockwise or counterclockwise? Okay, so let's think about all these questions. And let's work it out over here. So I'm going to start with the radius. The radius. Okay, so if we have an electron injected into the magnetic field, the radius of the circle that it's going to end up moving in is mv divided by qb. We derived that earlier, so we're just going to use it to make the calculation. Mass, 9.11, 10 to the minus 31 kilograms. Speed, 2.0, 10 to the 7 meters per second. Okay, divided by the charge, 1.60, 10 to the minus 19 coulombs. And then finally, B, which is the magnetic field strength, 0.010 Tesla. Again, I don't want to go too deep into the unit analysis right now, but every single thing that I plugged in here is in SI units. So what should come out is SI units of meters for radius. And what we actually get is 0.0114 meters. So what we want to do is round that off to two significant figures, and then also give the answer in centimeters. So in centimeters, this would be 1.1 centimeters. So it actually moves at a really, really small path. Imagine a circle with a radius of a centimeter, yet this particle is moving at a speed of 2 times 10 to the 7 meters per second. So it's still moving incredibly fast, but it's moving in a really, really tight circle, and that means it's going to have to make a lot of trips around that circle every second. Okay, the next question was about the frequency, and we can call this the cyclotron frequency. And here's what we're going to get. Okay, so frequency is given by QB divided by 2 pi m. And let's plug in what we know. The charge, 1.6, 10 to the minus 19 coulombs. B field strength is 0.10 Tesla. And then divide out 2 pi times the mass, which is 9.11, 10 to the minus 31 kilograms. Okay, so what does this come out to? If you calculate this, it's 2.8 times 10 to the 8 hertz. Now, how about we just real quick go through the units on this one? Okay, it's really not obvious why coulombs times Tesla divided by kilograms give you hertz, so let's do that. We have coulombs times Tesla over kilograms. And let's start with this. A Tesla is the same as a Newton per amp per meter. We discussed that in the previous lecture. And then that's multiplied by a coulomb on top, divided by a kilogram on the bottom. Okay, so I could write this as a coulomb times a Newton divided by a kilogram, and amperes and meters can also go to the bottom. And then let's also think about how units of newtons can be broken down. Well, when we have a newton, we can think of that as a kilogram meter per second squared. On the bottom we have kilograms, and then we have amperes, which can be thought of as a coulomb per second. And then we have meters left over. Okay, so we can do a lot of cancellation. Kilograms, coulombs, meters. And so here we have 1 over second squared over 1 over seconds. That's kind of confusing to look at, so if I have 1 divided by 1 over seconds, that's like putting the seconds on top again. That's seconds over seconds squared, or 1 over seconds. And that's what a hertz, actually is, inverse seconds. Okay? So what is this number telling you? Well, here, 2.8 times 10 to the 8, we can write that as 280 million. 280 million what? Well, 280 million full circles every second. So this is kind of amazing. The electron is moving in a tiny little circle. The radius is about a centimeter. Probably not too different from what I just drew. But it's moving so fast that it completes 280 million full circles every second. So imagine something moving in this circle going around 280 million times every second that passes. That's what's going on here. So the next thing is the direction. So I know it's moving in a circle based on everything we talked about up until this point, but what kind of circle? Clockwise, counterclockwise? How do I know? Well, go back to the picture. We have a magnetic field pointing inwards. So there's B. We have a negative charge, it's an electron after all, which is moving to the right. Let's first figure out what kind of force this charge is feeling. And the way we do this, as always, is with the right-hand rule. The right-hand rule says you take V, you take your fingers of your right hand, point them in the direction of V. You curl them in the direction of B, which is into the page. So now your thumb is pointing up like this, but the charge is negative. So you have to flip that so your thumb is pointing down like this. So the right hand rule tells us that the force is going down. And that actually tells us exactly which way it's moving because the force is pointing towards the center of the circle. So I can actually now draw that circle it's moving in, where that's the center. And it looks like, if we just kind of follow this path, looks like we're going clockwise. Yeah? So the charge moves clockwise. Okay, so again, the reason we were able to determine that it moves clockwise is by thinking about what direction the force goes in. That allows you to sketch out the circle it moves in, and then you can see that it's moving clockwise. That's how that works. Okay, so that was the example. Now let's take this a step further. We have the idea that if you take a charge and you put it into a magnetic field so that it's moving perpendicular to the magnetic field lines, that it's going to move in a circle. It's going to move in a circular path. Turns out, particle that you put into a magnetic field, it doesn't have to have a velocity that's exactly perpendicular to the field lines. So let me show you what I'm talking about. Let's say I have a charge Q, okay, and I have a magnetic field, and that's shown in the red lines here, which is pointing straight to the right. But instead of having my velocity go perpendicular to those magnetic field lines, instead I'll just have it go at some random angle that's not necessarily perpendicular, like this, okay? So now what we have is a scenario where the velocity here has components, okay? I can think about it in the following way. I can think of V parallel as being the component of my velocity that's parallel to my B field lines. So it's going in the same direction as my B field lines. That's right here on the bottom. That's V parallel. At the same time, I'm going to have a V perpendicular, which is the component of my velocity, which is perpendicular to the B field lines. Okay, so what do we know about the way magnetic forces work? Well, if I have a velocity that's parallel or going the same way as the magnetic field, that's not going to create a force. It's only when I have a velocity perpendicular to the magnetic field when I actually have a force. So there's actually no force at all in this direction, in the direction of my B field, which is telling me that at least this component of velocity, V parallel, is constant. So as far as the way we move along the B field lines, it's constant velocity. However, if we think about not the direction parallel to the B field lines, but perpendicular to it, we know already how the charge is going to move. It's going to move in a circle. Okay, so really think about that. What does it mean for something to move in a circle in one plane, but move at a constant velocity perpendicular to that? Well, as I'm going to show you, the overall trajectory is shaped like a helix. It's a spiral. So it's moving in a circle, but that circle is also kind of moving forward. It's a spiral or a helical pattern. So this is the kind of motion we're talking about in general when you have a charge moving in a magnetic field. It's a spiral, and this is like a pretty complicated trajectory. So it's in some ways surprising that simple charge moving in a uniform B field can give you this kind of trajectory, but that's how it works. And so to dive deeper into the details here, what I want to do is show you an example. Okay? We have a proton whose charge is 1.6 10 to the minus 19 coulombs, and whose mass is 1.67 10 to the minus 27 kilograms. We're going to inject this into a uniform magnetic field with a speed of 1.3 times 10 to the 7 meters per second. And it's going to be at an angle of 75 degrees relative to the B field lines. Okay, so in other words, in this case, my B field is going straight to the right. Imagine that when the proton enters the B field, it's moving like this at a 75-degree angle relative to the B field lines. Okay, so the B field has a magnitude of 1.5 Tesla. We're going to calculate two things here. We're going to find the radius and the pitch of the helical path that the proton moves in. Okay, so as far as the radius, this is pretty simple to understand. If we draw out the helix, the radius is just the distance from the center of the helix to the outer edge of the helix. So just like for a circle, it's just the distance between the center and the outer edge. As far as this thing called the pitch distance, this would be the distance between loops, okay? So how much distance do I have to travel to get from one loop of this helix to the next one? That's the distance P shown in the diagram. Okay, so we're going to get both of these numbers. Okay, so now to take this over to the document cam to work it out. And we'll start with this. It's going to be really important just to have this fleshed out before we do anything else. Let's break V into components. So I'm talking about V parallel, V perpendicular, that sort of thing. Well, remember our velocity vector looks like this, and it makes some kind of angle with respect to the B field lines. That's theta right here. So V parallel is this leg of the triangle down here. V perpendicular is this over here. So again, since my B field is going to the right, this is parallel to that, and this is perpendicular to the B field lines. So let's work it out. How do I get, let's say, V perpendicular? Well, that would just be the speed times sine of the angle, because V perpendicular is the opposite side in this right triangle. Okay, and then V parallel would be V times cosine of the same exact angle. Okay, so now we're gonna grab that whenever we need it. Now I want you to imagine this. Okay, it can be a little bit hard to visualize this helical motion. So what I want you to do is break it up into parts. Okay, let's take the perspective where we're looking into the B field lines. And here, just on this drawing over here, I'll show that the B field was going to the right. What I want you to imagine is you're looking from this direction directly into the B field lines. You're looking that way. So here's what you're going to see. If you're looking into the B field lines, then you're going to see them coming out at you. So I draw B coming out of the page now. And I would also see a charge Q, which has some velocity, but it's not the full velocity. It's only the perpendicular component that I'm going to see if I'm looking into the B field lines. I'm only going to see V perpendicular. Okay, so this is really the idea. I have V perpendicular, B field lines coming out at me if I take this perspective. And what does that look like? Well, I know that at least in this plane that I've drawn, the proton moves in a circle. Why is that? Because again, I have a velocity perpendicular to a B field. And let's run through the math of that. The net force in the radial direction, what does that equal? It equals the mass times the acceleration in the radial direction. And okay, let's work those out. Well, for the force, this is just the standard magnetic force, where we have Q times, in this case, just v perpendicular. Only this velocity component matters for what we're doing here. Times b times sine of the angle between v perpendicular and b, but that's 90 degrees by definition, right? Because this is only the component perpendicular to b, so we're talking about a 90-degree angle. What does that equal? The mass times v perpendicular squared divided by r. So what have I done here? I've taken the magnetic force and I've equated it to mv squared over r, but crucially, I'm talking about v perpendicular only in this case, because v parallel doesn't give me a magnetic force. What I'm going to do then is solve for r, because we, of course, want the radius. And let's also just take a quick note that sine of 90 degrees is 1. So when I solve for r, I'm going to multiply on both sides by r to put it over here on the left. I'm going to divide on both sides by q v perpendicular b. So here's what I get. N v perpendicular on top divided by qb. Okay, so my radius is, if I plug in v perpendicular is v sine theta, my radius is m v sine theta over qb. And again, this is just a statement that since my velocity is not purely going perpendicular to the b field, I need to grab this component of it, v sine theta, to make this work. All right, so then it's time to plug in the numbers. The radius is equal to the mass of my proton, which is 1.67, 10 to the minus 27. Units are kilograms for mass. I have to take the speed now, which is 1.30, 10 to the 7 meters per second, and then multiply by sine of the angle, which is 75 degrees. Divide out q times b. Q is 1.60, 10 to the minus 19 coulombs. B is 1.50 Tesla. Again, the units are kind of messy here. You can do the analysis to show that this works out in meters. I'm going to skip over that for now and just do the result. We have 0.08738, keep 3 sig figs, meters. And of course, it might make more sense to write this in centimeters. We have 8.74 centimeters. So that's the radius of this helical path that our proton is moving in. 8.74 centimeters. All right, let's do a little bit more with what we have here. Let's think about the fact that, okay, I haven't even shown you guys the circular path that our charge moves in. So I'll do that right over here. Okay, so if I want to take V cross B, okay, so fingers going up and then curling them out of the page in the direction of B, then my force is going to be going to the right, like this. So I can't actually draw the whole thing because I didn't make myself enough space, but there you can kind of see what the circle is that this thing is moving in. And so if we think about V perpendicular, that's basically how fast we're moving in this plane, in this circle. That's just the distance we travel divided by the time. And of course, if we're talking about one full circle, the distance we travel is 2 pi r, and the time is the period. And so what I'm trying to do here is get the period because it's going to be used later. So what do I have? I have, if I'm taking this and solving for t, so multiply on both sides by t, divide on both sides by v perpendicular, we get 2 pi times r divided by v perpendicular. So t is equal to, let's write it as 2 pi over v perpendicular, and then plug this expression in for r. It's n v perpendicular divided by qb. Cancel out v perpendicular. What do we get? 2 pi m over QB. So it actually has the same exact period that we derived before, 2 pi m over QB. We're going to use that. And in fact, we're going to put a number to that to get the period. So let's plug in the mass, 2 pi times 1.67, 10 to the minus 27 kilograms, divide by Q, 1.60, 10 to the minus 19 coulombs, V, 1.50 Tesla. Okay, so this is a time, it's going to come out in seconds. 4.37 to 10 to the minus 8 seconds. So this is the time to complete one loop. That's what the period is. And it's a tiny amount of time, indicating this thing is making a lot of loops every second. It's moving very fast. Okay, so what have we done so far? We started by looking, or taking the perspective where we're looking into the B field lines. And what we see in that plane is the charge moving in a circle. Now let's take a different perspective. So here, let's consider the motion of the proton in the direction that's parallel to the B field lines. Okay, so we already established that there's no force in this direction. Why is that? Because the magnetic force is QV cross B. So the force is always going to be perpendicular to both the velocity and the magnetic field. So if we're talking about the direction parallel to the magnetic field, then we can't have a force in that direction. So, in other words, proton moves with constant velocity. In this direction. Okay, we already found how much time it takes to make one loop. So that's actually very useful for us. Now we're going to think about V parallel. So how fast the proton is moving parallel to the B field lines. Let's just think about this as being a distance traveled divided by a time. And here, let's put on the bottom, for the time, the period. So that's the time it takes to complete one loop. How far does it travel parallel? Well, that's what we call the pitch distance P on our diagram. That's the distance between successive loops. So it looks like the pitch distance P is V parallel times T. And V parallel, as we said, is V cos theta. So we're doing V cos theta times T. The pitch distance, or the distance between those loops, is equal to V 1.3 10 to the 7 meters per second cosine 75 degrees times, so we're going to just plug in what we calculated for the period of the motion, which is 4.372 times 10 to the minus 8 seconds, which gives us, for the distance, 0.1471 meters. We're going to keep 3 sig figs in this case, and if we round this to centimeters, it's 14.7 centimeters. Okay? So that's the answer. Okay, so to go back to the picture, what this means is the radius, which is the distance between the center of the helix and the outer edge of it, is 8.74 centimeters. That's what we found for this. And then the pitch, which is the distance between successive loops, is 14.7 centimeters. Right? All right, so the next thing let's talk about is the Lorentz force. So what do we have so far? If you think back all the way to chapter 21, we have electric fields, and we know that if you put an electric charge in a field, in an E field, that it's going to feel some kind of force. We also know from this chapter that if you take an electric charge and it's in a magnetic field, in a B field, then it can also feel a force. So in general, an electric charge can be in the presence of both an E field and a B field. So you can have a magnetic field and an electric field at the same time. That's totally possible. And in that case, you want to think about the total force that's going to act on that point charge. What we call that is the Lorentz force. So let's review. We know that the electric force that a charge feels when it's inside of an E field is simply given by Q times E. Let's call that the electric force. We also know that the magnetic force that it feels is QV cross B. And in general, you can have both of these forces at the same time if there's an E field and a B field at the same time. So when we add those two forces together, we call that the total electromagnetic force. It's called the Lorentz force. Okay? So with that said, let's take a look at this. We have an electron moving in a region with an electric and a magnetic field as shown below. Okay, so what do we know about the magnetic field? That's B coming out of the page. What do we know about the electric field? That's E, shown in red, going to the right like this. The question here is, what is the direction of the Lorentz force? Okay, so for this one, let's just do it right here on the slide. Everything we need to know about the Lorentz force, we can sort of work it out conceptually. All right, so let's take this in pieces. First, we have the electric force, which is given by Q times E. Remember how this works. If I have a positive charge, then the force is in the same direction as the E field. If I have a negative charge, then the electric force is in the opposite direction as the E field. Well, in this case, I have a negative charge. An electron is negative, so the electric force that's going to be felt is to the left against the E field lines. Okay? So this part of the force, the electric force, is going to the left against the E field lines. Okay, if I want to know the direction of the magnetic force, well, that's going to be given by the right-hand rule, essentially. So let's think about it. QV cross B. My V, the velocity, is going straight to the right, and my magnetic field is coming out of the page. All right? So I have V going to the right like this. I'm going to point the fingers of my right hand in that direction, and I'm going to curl the fingers of my right hand in the direction of B, which is out of the page. So like this. Now my thumb is pointing down. Am I done? Is this the direction of the magnetic force? Well, no, because again, we have a negative charge. The actual direction of the force is going to go up. So what do we have? Magnetic force going up. So put those together. Electric force going to the left, plus a magnetic force going up. We don't have to really put a number to it, but what quadrant are we talking about? Okay, when part of my force is going to the left, and another part of my force is going up, we're over here. We're in quadrant 2. So Q2, quadrant 2 is the answer. Okay. Pretty much for the remainder of this lecture, what we're going to be talking about are different applications of this Lorentz force idea on particle physics. So how can we use electric and magnetic fields to get particles to move in exactly the way we want them to? Okay? So let's talk first about velocity selectors. What is a velocity selector? Well, this is just a device that only allows particles with a single velocity to pass through. So it selects for a certain velocity. It basically consists of a region with perpendicular E and B fields and two narrow slits. All right, so here, let's think about what's going on inside of this region. We have an electric field going down and a magnetic field going into the page. Now the specifics of that aren't super important, but notice how E is perpendicular to B. They're at a right angle with respect to each other. Then we have a narrow slit right here, and a narrow slit right here. So what happens is we take some kind of particle, and it's moving into the velocity selector. It's moving into it, and it moves into it by going through the first slit right here. Now the only way that that particle is going to get out is if it moves in a straight line. Okay, because let's say it takes a curved path. So it moves in here, and then it curves up. Well, it's not going to make it out because it's going to hit this wall right here. It goes into the velocity selector, and then it curves down. Also not going to make it through because it's going to hit that wall. The only way it's possible for this particle to get all the way through is if it just keeps going in a straight line. And so as it turns out, there's only one particular velocity that will work such that you just move in a straight line. Okay? And so what we're going to do is figure out what that velocity is. And the way we're going to do it is by saying, if it's moving in a curved path, if it curves up or down, there's obviously some kind of force acting on it that makes it curve up or down. But if it just keeps moving in a straight line at a fixed speed, we know there is no net force acting on it. In other words, the only way to get through the velocity selector is if there is zero net force acting on the charge. Okay? That's the idea. So here, let's kind of copy down what we had. We had the E field going down. We had the B field going into the page. And then we had a charge moving through this region, Q, which at first was going to the right. Now let's think about what the forces are here. I haven't said anything about what kind of charge we have yet, but let's just say, for the sake of argument, it's a positive charge. So that means we're going to have an electric force going exactly in the same direction as the E field, so that's going down. And then we're going to have a magnetic force determined by the right-hand rule, QV cross B. All right, so what do we have? My velocity is going to the right. My B field's going into the page. Looks like my thumb's going up. So my magnetic force would be going up. Now, keep in mind, if this were a negative charge, it'd be the same exact situation, except just flip FE and FB in terms of which one is going up and which one is going down. So it really actually works the same way. And again, we want this to move in a straight line. And that automatically means that the net force acting on it equals 0. And so what that is telling us is that the electric force plus the magnetic force equals 0. Another way of saying that is, if I add two forces together and I get 0, they have to have the same magnitude. In other words, the electric force is pulling it down just as hard as the magnetic force is pulling it up. So FE equals FB, at least in terms of magnitude. Okay, so let's work that out. The electric force is given by, here, let's on the side do this. The electric force is given by Q times E, and the magnetic force as a vector is given by QV cross B. So on the left side where I have my electric force, and I'm only thinking about the magnitude, I'm just going to write Q times E. So that's just the magnitude of that force. And on the other side of the equation, where I have the magnetic force, and I want the magnitude of that force, I'll take Q times V times B times sine of an angle. But what's the angle between your velocity and your B field? Well, it's 90 degrees. Okay, because one's going into the page, the other's actually on the page itself, so that's a 90-degree angle. Okay, so what we can then do is divide out the Q, so apparently it doesn't matter how much charge we have. Also note that sine of 90 is 1. And then we'll get that v, the velocity that we're selecting for, is e divided by b. So this is a really useful device because if you can sort of fine-tune the values of e and b, like how strong the electric and magnetic fields are in the velocity selector, you can make the particles come out with any velocity you want. You can select for any velocity you want just by changing e and b just to the right values. That's how it works. So that's where we came up with this expression: the velocity selected by the device is e divided by b. Okay, so let's keep going. The next kind of device I want to tell you about is something called a mass spectrometer. And a mass spectrometer is a device, well, that measures mass. In particular, masses of particles, like atoms or ions. And the way it does that is by accelerating those particles in a magnetic field. Okay? So there are a couple steps to this, so I want to work you through it. So the first is up here. In our mass spectrometer, we have a chamber where the ions are being produced. Okay? So we take some sample of the atoms that we want to study, we put them in here, and then we ionize them, which means we're stripping electrons away from them to take what was a neutral atom with no charge and make it charged. In this case, it will have a positive charge because we're taking away the electrons. So the way we ionize is by taking away one electron per atom, making it positively charged. The way you specifically do that can vary, but this is where the particles become ionized and they get a positive charge. Okay? So after that, they're going to move into a velocity selector. So here's the idea. When they're in this chamber, before they move into the velocity selector, there's no particular velocity that they have, right? They're all kind of moving with completely random velocities in completely random directions. It's a mess. But once they go into the velocity selector, what comes out is going to be one specific velocity. That's really important. So remember how this works. We have an E field going down and a B field going into the page, basically just, an E and a B field at right angles in this region here. And then, again, the particles come out of the velocity selector, and now what happens? Now there's no more electric field. We're only in a region with just a magnetic field. And we're going to call that B prime. Okay, so let's keep those two things straight. B is the magnetic field in the velocity selector, and then B prime is the magnetic field out here after things leave the velocity selector. So let's think about how a charged particle would move after it exits the velocity selector. Well, it's going to be moving perpendicular to the B field out here, which means it's going to be moving in a circular path. Okay? It's going to be moving in a curved path like this. Okay? So if we follow that curve around, this half circle, and then we put something right here called a particle detector. So this is just measuring whether or not a particle hit the detector. So it could say, yes, something hit here, nothing hit, nothing's going to happen. But it just basically registers that a particle hit the detector. And it can tell you exactly where it hit. In other words, we can measure how big of a circle this is, right? So if everything's hitting up here, it's a small circle. If everything's hitting way down here, it's a bigger circle. We can actually measure the radius based on where things are hitting the detector. Okay, and what I'm going to claim is that through all of this, you can determine the mass of whatever you put in this first chamber. Okay, it's kind of a complicated process. You have to send it through a velocity selector, you have to send it through a magnetic field, then it has to hit this particle detector. But my claim is, when it's all said and done, you can measure the mass. And let me show you how that works. Okay, so let me just do a couple derivations for you. So remember, we inject some ions into this velocity selector. How fast are they coming out of the velocity selector? Well, we already worked that out. Ions will come out of the velocity selector at speed, let's call that speed V, equals E divided by B. So it just depends on how strong the E field and the B field in the velocity selector actually were. Okay, so then, after the ions leave the velocity selector, basically what's happening is they are traveling perpendicular to a uniform B field. And we'll call that B field, as we said earlier, B prime, to differentiate it from the one in the velocity selector. Okay. So let's apply Newton's second law to analyze what happens when they're just in this uniform B field after leaving the velocity selector. Well, we know that the net force is equal to mass times acceleration. We know we have got some kind of circular motion going on here. So let me actually take note of that, circular motion. And what do we have for the force? Well, we have Q times V times B prime times sine of, in this case, 90 degrees, because as we just said, they're traveling perpendicular to that uniform B field. So that's how you write out the magnetic force. On the other side of the equation, we have M times A, and that acceleration is V squared over R, because we're dealing with circular motion. Okay. Now in this case, I want to solve for M. I want to solve for the mass of these particles, because I know everything else. Solving for M by multiplying through on both sides by R and dividing on both sides by V squared, it's going to give me this. I have QV B prime. Sine of 90 goes to 1, so let's just do that. I'm going to have R here, and then I'm going to have a V squared on the bottom. So in summation, I have QB prime times R divided by V. And then I'll just plug in what I know V is. That's just the velocity that we select for. So that's going to be QB prime times R divided by E over B. And I can write that as Q B prime times B times R divided by E. Now, let's make some sense of that. M is the mass of the particles that I'm trying to measure. As long as I know the charge, which I do because I know I've ionized each one and I've given each one a just positive charge. I know what B prime is because that's just whatever I set the magnetic field to. I know what B is. I know that's what I set the magnetic field in the velocity selector to. I know E, again, just something you can dial in using this device. And then R is the radius of the path. So that's really the fundamental thing. The mass and the radius are related. They're proportional to one another. M is proportional to R. Meaning, okay, the more massive the particles are, the bigger their radius will be when they move through this magnetic field. And it makes sense. A lighter particle is going to move in a smaller radius. And it's that radius which is really telling you something about the mass of those particles. Okay, that's the idea. So with that said, let's do an example using a mass spectrometer. So let's say we've got a mass spectrometer containing a chamber where the atoms are ionized by heating. So maybe we can cause them to be ionized just by getting them to a really high temperature. And in this process, a single electron is removed from each atom. Okay, so each one is going to have a positive charge. Now these positively charged ions enter this velocity selector, where the electric field is 4.5 10 to the 3 newtons per coulomb. This magnetic field is 2.5 10 to the minus 3 Tesla. And before we do the next part, let's just say, what is the speed of the ions that are leaving this velocity selector? Okay. Then let's look at the next part. After the ions leave the velocity selector here, they enter this region where there's a magnetic field, which we're going to call B prime, which is 1.65 Tesla, much stronger than before. Okay, there is a strong signal from the detector 27.3 centimeters below where the ions emerged. Okay, what is the mass of the ions? That's the question. What is the mass of these ions? Well, one thing I want to point out is this distance is just a diameter. It's the diameter of the circle we move in. And I guess now we can make the calculation. All right, so in this case, we want to calculate the speed of ions leaving the velocity selector. Well, that's given by E divided by B. That's how a velocity selector works, as we saw earlier. And E is going to be, in this case, 4.50 10 to the 3 newtons per coulomb. And B is going to be 2.50 10 to the minus 3 Tesla. Again, the units get a little funky here, but as long as everything is in SI, then the speed comes out in meters per second. And that's going to be 1.8 10 to the 6 meters per second in particular. Okay, so let's look at the next part. We want to figure out the mass. And here, find the mass. Now, we already worked out what the expression is. It's going to be Q times B prime times R divided by E. And let's just take note that if one electron is removed from each atom, and remember that an electron has a charge of negative 1.6 10 to the minus 19 coulombs. Now we're just going to have the positive version of that, because we took away negative charge, so we have positive charge. And that's going to be positive 1.6 10 to the minus 19 coulombs. So that's going to be the charge of each one of these ions that we're trying to get the mass of. So to get the mass, what we're going to have is Q, which is 1.6 10 to the minus 19 coulombs. Then we're going to have B, which is 1.65 Tesla. That's the one of the magnetic fields. The other one is 2.5 10 to the minus 3 Tesla. That's B and B prime. Then the radius of the path, well, we're given the diameter, so radius is half the diameter. And that's going to be a half of 0.273 meters. And then we're going to divide by the electric field, which is 4.5 10 to the 3 newtons per coulomb. Okay, so again, that's really getting messy with the units. Let's just use the rule that if you put the units in SI going into the calculation, they come out in SI at the end, so we have kilograms. And it actually works out to a nice round number, 2 times 10 to the minus 26 kilograms. Okay, so kilograms, that's a fine way of talking about mass. I actually want us to do a quick unit conversion here. And we're going to get this into something called atomic mass units. So let's explain what's going on here a little bit. So an atom is a collection of protons, neutrons, and electrons. The nice thing about the masses of these particles is electrons have tiny mass compared to either protons or neutrons. So you can basically ignore the mass of electrons. That doesn't really factor into things. And that's also good because since we removed an electron in this process, we haven't really changed the mass that much, not in any appreciable way. Also, protons and neutrons basically have the same mass, and that mass, I'm going to write it for you, is 1.67 10 to the minus 26 kilograms. And what we call this is an atomic mass unit given by lowercase u. So what have I just done? I've multiplied by a conversion factor that says one atomic mass unit is 1.67 10 to the minus 27 kilograms. Again, that's just the mass of a proton or a neutron, basically the same thing. Now, when you do this calculation, you get 12 atomic mass units. And that's telling you that the total number of protons and neutrons is about 12. So we can actually say with pretty good confidence what kind of atom this might be. What if 6 of those are protons and then 6 are neutrons? Well, an atom with 6 protons is called carbon. And when it comes in this variety, where it has 6 neutrons coming along, we call this carbon-12. Okay, so I can actually, this is basically a summary of a basic experiment you can do to detect that you've got some carbon-12 coming out of this device. And then there's going to be a follow-up to this. Okay, let's consider that same exact mass spectrometer from the previous problem. And again, what happened in that previous problem is we detected a really strong signal, a distance of 27.3 centimeters below where the particles emerged. Okay, and we've determined that what we have here are carbon-12 atoms with a mass of 12 U or 12 atomic mass units. Okay, now let's say that we don't just see that one signal. We see also a weaker signal at a different position, which is 31.9 centimeters down here. So let's figure out what is the mass of these particles that are hitting this spot. Now we know intuitively that they're going to be more massive than before, because if the circle is bigger than before, it implies the particles are more massive. But exactly how much, let's figure that out. Okay, so to continue on our previous work, let me just write the formula we derived, where the mass that we're detecting is Q times B prime times R divided by E. And then let's just sub in for the radius diameter over 2, Q times B prime times diameter over 2E. Okay? And look, if we rearrange things a little bit, let's say we divide out the diameter, we have M divided by D is equal to Q times B prime over 2E. And let's take a look at everything on this right side because, well, Q. Every single ion is going to have the same charge because for each one of them, we're taking one electron away. Each ion is going to be moving through the exact same fields, B prime, and E, so that's all the same, and then there's the number 2. So we can actually say that this is a constant. Right? So the ratio of mass divided by diameter for that path it moves in is going to be constant because all these numbers are constant. So look, if mass divided by diameter is the same for any 2 runs of this experiment I do, I can compare 1 and 2. M1 over D1 equals M2 over D2, in other words. And what I'm looking for is M2. That's M1 times D2 over D1. Let's calculate that. Okay, so the mass M1 I want to put is 12 atomic mass units. And D2 is going to be 31.9 centimeters. That's just what we were given. And D1, also what we were given, is 27.3 centimeters. Okay, if you calculate this, what you're going to get is 14 atomic mass units. And I'll just tell you what this most likely is. This is what we call carbon-14. It's another type of carbon which has the same exact number of protons, because remember, in chemistry, the number of protons is really what makes an atom an atom. So all carbon atoms have 6 protons, but it's possible to have, 8 neutrons in this case. And what we call this is a different isotope of carbon than what we had earlier. Okay, so that's actually one use of a mass spectrometer, is you can detect different isotopes of the same atom. Okay, and again, that just means different numbers of neutrons for the same type of atom. That can be detected using a mass spectrometer. So that's the question. The answer was 14 atomic mass units. Okay. Next thing, cyclotrons. Okay? Now what a cyclotron is, it's a device that's used to accelerate charged particles to really high speeds. That's the whole point of a cyclotron, is you're trying to get particles to really high speeds. This is how it works. So the basic setup is this. You have a really strong magnet with a north pole up here and a south pole down here. And what that is going to create is a magnetic field which points down like this. Okay, a really strong magnetic field pointing down like this. Okay, then we have this cavity where there are 2 sides and each one is shaped like the letter D. And they're separated by a tiny little gap, a really small gap. Okay. Now what is going on in the gap? Because this is important. What we have is an AC voltage source. Okay? And basically what this AC voltage source does is it creates a strong electric field inside of the gap. Alright? So here's what's going on. We start off by injecting particles into the very center of the cyclotron. They start over here. And they start off not moving that fast. Okay, actually they can start off with 0 speed. Okay, but if they're in the gap, they're going to be accelerated across the gap, and then after that they're going to be moving in a pretty much uniform magnetic field. Okay? What does a uniform magnetic field make these charges do? It makes them move in a circle. Okay, so they move in circular paths. Okay? But again, each time the particle passes through the gap, it's going to get a little kick from the electric field. It's going to move a little faster from the electric field. And so, in a pretty short amount of time, the size of this circle is getting bigger and bigger and bigger as the particles are going faster and faster and faster. They're spiraling outwards from the center. And by the time they reach the edge of the cyclotron, they can be moving really fast. Okay? So let me show you what we're talking about here with an animation. Okay? So this is the top-down view of the cyclotron. And so we have these 2 D-shaped cavities that the charged particle gets to move through. We have a magnetic field, which is going into the page. And then we have an electric field across the gap. Okay, and that's shown in red. Right, so let's think about what happens. If I have this electric field in the gap, then what's that going to do to my charged particle? If it starts right here with no speed, it's going to be pushed to the right, and it's going to speed up a little bit. But then, once it gets to the magnetic field, now it's going to move in a circle, and now it's going to end up over here. Now this part is really important, because notice how my electric field is still going to the right, and my charged particle is moving this way, to the left. Okay, if it enters this electric field as it's currently shown, it's going to start to slow down, because the electric field is going to push against its motion. So we need the electric field actually to flip, go the other way. And we can do that with an AC voltage source, where basically the voltage is flipping back and forth, makes the electric field flip back and forth like this. Okay, so now, once my charged particle goes back in the gap, it's going to be accelerated even more. So now it's moving even faster, it's moving in a bigger circle once it gets over here. But what do we need to happen? We need the electric field to flip back the other way again, so that now this can push the particle and cause it to accelerate even more. Okay, moves in another circle, or another half circle, ends up over here. Again, we need the electric field to flip back the other way so it can accelerate even more. And then eventually it just flies out of this cyclotron. So it's not going to do this forever. It's going to only do it until it gets to the edge of the cyclotron. But the point is, by the time it gets to the edge of the cyclotron, it can be moving pretty damn fast. And so the next thing we'll do is make a calculation. So we have a cyclotron shown here with a uniform magnetic field of 2 Tesla and a radius of 0.45 meters. There's a potential difference, or a voltage, delta V, 14,500 volts, in the small gap between the two V-shaped cavities. This proton, whose mass and charge are given here, is injected into the center of the cyclotron with 0 initial speed. Okay, so we have a number of questions. How much kinetic energy will it have when it reaches the outer radius of the cyclotron? How many times is it going to pass through this gap during the motion? And how long is it going to take to reach the outer radius of the cyclotron? So let me just again show you what the motion looks like. It's this sort of spiraling outwards and gradually getting faster that our charge does, and eventually just exiting the cyclotron. So let's see it one more time. So let's answer these questions. We have all the information we need to do this. Now, the first question concerns kinetic energy. So remember that kinetic energy is given by K is 1/2 mv squared. So if the question is, find the kinetic energy at the end of the motion when it exits the cyclotron, I need to know the speed. Okay? So I need to find the final speed. Well, when this thing is moving in a magnetic field, we know how to describe that. We've seen a number of problems involving a charge moving in a magnetic field in a circular path, and that's pretty much what's happening here. And so the way we do this is we take the net force in the radial direction of the charge. That equals the mass of the charge times the acceleration of the charge in the radial direction. And so the force is a magnetic force. It's given by QV times V times sine, in this case, 90 degrees. That is the angle between our magnetic field and our velocity. So here, let me just indicate that what I'm doing is F equals QV cross B for the force, and that equals mv squared over r, because that's the acceleration of something moving in a circular path. All right, what are we trying to find? Velocity, or speed, I should say, v. So if we take the fact that sine of 90 goes to 1, if we divide by this v, okay, we're just going to have v over here instead of v squared. If we multiply it by r, we're going to get rid of it here and put it over here. And then if we divide by m, we're going to get rid of it here and put it over here. So v is equal to qb r divided by m. That's the speed. In other words, what is this telling us? As the radius gets bigger, okay, as r increases, so does the speed. That's exactly what we're seeing happening in this cyclotron. As it spirals out to a bigger and bigger radius, it's going faster and faster. So the kinetic energy, therefore, is given by 1/2 times the mass times v squared, and we're going to put this in for v. qbr divided by m, and we're going to square it. So we have q squared, b squared, r squared, divided by 2 times m. That's what that works out to. And so let's put a number to that. Q is equal to 1.6 10 to the minus 19 coulombs, square it. B is equal to 2 Tesla, square it. And then if we're interested in the final kinetic energy, we want to use the outer radius of the cyclotron, which is going to be 0.450 meters, square that. Then we divide by 2 times the mass, which is 1.67, 10 to the minus 27 kilograms. And this gives us 6.208 times 10 to the minus 12 joules. And I guess we would round that to 6.21, 10 to the minus 12 joules with 3 sig figs. Okay, so we answered that question. The next question is, how many times is it going to have to go through that gap in order to get to this energy? So here, let's think about what happens each time the proton goes through the gap. Okay? It's going to gain some kinetic energy. And we'll call that delta K. It's gaining kinetic energy because, again, the electric field is pushing it to a higher speed. And we can calculate what that delta K is based on conservation of energy. Which says delta K plus delta U for this proton equals what? 0. Because energy is conserved overall, so the net change is going to be 0. Delta K in this case is going to be minus delta U, just subtract delta U on both sides. And then remember from chapter 23, that delta U, the change in potential energy for a charge moving through a potential difference, is minus Q times delta V. Or Q times delta V is what I'm talking about. Okay? Okay, so let's put a number to that. So what we're going to have is the charge, 1.6, 10 to the minus 19 joules. The delta V is the potential difference in the gap, which we were told is 14,500 volts, and a volt is a joule per coulomb. Strictly speaking, this has to have a negative sign if we're going to accelerate this thing rather than slow it down. But anyway, delta K is going to be, if you calculate this, 2.32 10 to the minus 15 joules. Okay, so here, what do we have? The total kinetic energy that the electron, or the proton, eventually comes up with is this, and then each time it moves through the gap, it picks up this much. Okay, so here, let's write an equation that says K, the total kinetic energy of this proton, is n, the number of times it had to go through the gap, times delta k, which is the kinetic energy it picks up each time it goes through the gap. So n is equal to k over delta k, which is 6.21 10 to the minus 12 joules, over 2.32 10 to the minus 15 joules. And what does this give us? This gives us 2,675.8. And so that's the number of times it goes through the gap, but strictly speaking, we round this to 2,680. So that's how many times it needs to actually go through that gap to get to this final energy. Okay, so the animation I showed you actually greatly understates how many times it goes through the gap. It goes through it thousands of times. Okay? So the next thing is, how long is it going to take to reach the outer edge of the cyclotron, and after that it's just going to fly out? Well, here, let's start by doing this. Let's think about the period. Let's think about the period of the motion, which is how long does it take to go in a circle once? The way we think about this is speed is distance over time. And so v is equal to 2 pi r, one full circle, divided by t, a period. Okay, t, the period, is 2 pi r divided by v, which means the period is, we can write this as 2 pi divided by v. Let's not do that. Let's write this as 2 pi r times the expression for v that we came up with up here, which was qbr divided by m. I'm sorry, guys. It's been a long day. Let me, okay, so v is on the bottom, right? So I have 2 pi r, and v is qbr over m, but the mass goes to the top, and then qbr goes to the bottom. That's what I was trying to do. And the radius drops out, and we have 2 pi times the mass divided by qb. That's the period. And notice the period only depends on the mass, the charge, and the strength of the magnetic field, which are not changing. None of those things are changing. So this is a constant period. So it doesn't matter if it's moving really slow and it's at the center of the cyclotron just starting out, or if it's moving really fast and it's at the outer edge, the period is always staying the same. Okay, so let's actually put a number to that period, which is 2 pi times the mass, 1.67, 10 to the minus 27 kilograms, divided by Q, which is 1.60, 10 to the minus 19 coulombs, and then B, which is 2 Tesla. So we get a period here, which is equal to 3.279 times 10 to the minus 8 seconds. And then to wrap this up, let's think about this. The total time is not that. This is the time it takes to make one circle in the cyclotron. The total time is going to be this. Delta T is equal to, well, I could take the number of times that I go in a circle times the period, and that should give me the total time, right? Because each circle takes this long, multiplied by the number of circles I make, gives me the total time, except, here's the problem. Up here, n is the number of times we went through the gap. we go through the gap twice in each circle, right? So if I go around a half circle, I pass through the gap once, and if I go around a complete circle, I pass through the gap twice. So I'm going to put this 1/2 factor here, which just indicates, again, that the charge goes through the gap 2 times every period. So then our total time, which I'm calling delta t here, is 1/2 times n, the number of times we went through the gap, which was 2,675.8, just pure number. And the period was 3.279, 10 to the minus 8 seconds. So the total time is 4.3869. Keep 3 sig figs, 10 to the minus 5 seconds, or round that to 4.39, 10 to the minus 5 seconds. So that is how long it takes to get to the outer loop of the cyclotron to that final speed. So it's still a tiny fraction of a second, but that's the answer. Okay, so I think, I think we'll just leave it here for now. We still have more to do, which we'll cover in the next lecture for chapter 27, and that's going to involve something called magnetic torque. So stay tuned. I'll see you next time for magnetic torque. Again, stay safe and healthy out there. I'll see you next time.